Because I checked the view, it's all me. It's just like 2-3 views per video. So I'm just wondering. Okay, do you guys have a chance to work on the problem set, the laptop one? Anyone who looked at it?
Yes.
No, not okay. All right. Okay, so today I'm gonna spend like almost half a class going through that problem sets, and I received some feedback last time saying I went a bit too fast, so I will go back and go through some of the concepts. So today the first thing I'm gonna talk about is how to apply a machine learning model. This means like the standard workflow of what we do when we train a model. Secondly, I will go through the regression homework. This one. Okay, I'll go through it quite detailedly and hope you guys can follow what I'm doing. And then afterwards, I will be going through the another key concept called classification. Okay. Is this a bit okay, never mind. Okay, the first thing with machine learning workflow, it's something like this. So machine learning is quite a standardized process, and if you do it like for many times, you see the steps are quite similar. Someone actually built an automatic machine learning pipeline. So he wants to do something that you fit in the data, it just split to train and test automatically, and then it just selects the model for you, okay? And then it will just find the most optimized parameters and just output the model and say, okay, this is the best the computer can find. Okay, so I think it's doable, and I'm quite sure in the future you might not need to build model yourself anymore. Someone will build like a package and you just stream the data in and just automatically come up with something. But I think if you want to do well in the field, it's important for you to understand what's going on inside and understand why some model outperform the other one. Because if you ask the machine to automatically do it for you, you can't really explain the pattern and you can't gain any knowledge by building the model. Okay. So every machine learning model goes through a workflow like this. Okay, so you have the data. It doesn't have to be in a database, but it can be like web data or just raw data. We always go through a step to transform it to something useful. And then almost certainly it will transform into a structure like this. So a tabular data with this is train X, that is a list of features in columns, and the labels, which is just your train Y, which is it can be like the magnitude, or it can be a binary label like 1 or 0, or it can be multi-class. So the example for binary would be like boy or girl. Okay, for multi-class, it can be like categorizing e-commerce product. So like jeans, blazer, computers, etc. For magnitude, it can be like house price or car price, etc. Okay. Okay, so I've summarized 7 steps in the machine learning model training. Okay, the first step is just the preparation steps. Say you have like a problem you want to solve. So first thing is you have to understand the problem. So whether or not it's a classification or a regression. Okay. And then secondly, start to get more interesting is where you can get the data. Okay, if you work in a big company, you probably have too many data. Okay, but let's say you are just an individual. Let's say you want to buy a laptop and you want to find the best price or the fair price of the laptop. Then you don't have a database to get. You have to go online and find the source. So in this case, web scraping might be the solution for you. Okay. And the third step is understand the type of label. Okay. So I just mentioned we have like multi-label, binary class, and the real value, which is the like house price, etc. And then we have something called the evaluation matrix. Okay. Anyone know what's evaluation matrix? Evaluation matrix is like the R square. So the score you build the model, and if you're doing classification, it's basically how accurate your model predicts. Okay. And anyone have any clue why do we need an evaluation matrix? Yeah, you have to evaluate the performance of the model, and if you have a parameter that can tune or you can play around with the data, there's a standard that you can maximize. Okay, so if you remove a column, you see the score increase. Does mean the model improve. Okay, so it's very important to have some like evaluation matrix. Okay. Okay, after the preparation, what do we need to do? Okay, we understand the question, understand the data. So the next thing is we have to clean the data. Okay, and we've spent like the last 3 weeks learning how to clean data, how to make use of pandas and fill in NA, shape it to different columns, etc. So I think one very important point is transform to tabular data. If you do a lot of machine learning, basically every single problem can be transformed to a shape like this. Okay. So it has to have a column called label, and has to be a lot of data, which is the features. And then, okay, after we change it to a shape like this, what's the next step? Will you do? Exploratory. I think the first thing I would do is just split it to testing data and training data. Okay. And then after that, you can do the exploratory data analysis. And what I mean by this is what we learned a few lessons ago: the visualizations and find out the correlation matrix. Okay, that one. If you don't have any domain knowledge of your datasets, you have to rely on those to find the correlations and to understand what the data is about. Okay, and then after you've done step 3, you can go to like step 4, which is just quickly build a model. Okay, and then you can quickly evaluate it, do a cross-validation check to see if it generalizes with the unseen data. And then after that, we have something called feature selections, model selections, and hyperparameter search. Okay, does the term sounds familiar to you or very strange? Okay, so what's meant by feature selection is to select the right column for you. Let's say after I build the laptop model, if the performance is very bad, okay, I do cross-validation and the score is very inconsistent, then you have to find which column you can remove, or you can do a PCA to compress the data sets, and you can keep on running the model and to see if you can get a better score.
Normally, how accurate is PCA? Is it better than I just search by myself?
I would say normally it's quite similar than using PCA and you drop it manually, but PCA is a lot faster.
Okay.
So if you don't care about the variables, you just do PCA.
Okay.
Yep. Any questions so far? Okay. Okay. Let me make this smaller. Okay, so this is how the automated workflow of data of machine learning looks like. So you have a data set, and then you just split it to X-train and Y-valid, and then X-valid data sets. So you have three things, or four things. So X-valid, X-train, Y-train, and Y-valid. Okay. And for X-train, which is the features we care about, we have different route for like numerical, categorical, or text data. For categorical, we tell if it's a binary label, or if it's like multi-class label, and then you put it into a stacker, and it just chooses the right the right decomposition method for you, and you can select the feature. And that's how the automatic machine learning works. I also mentioned something called model selections and hyperparameter search. Okay, and what it means by model selections is after you have selected all the features, you can go through every single model. You can just write a loop through every single one of them, and see which one perform better. Okay, but for every model, you have different parameters. So let's say for rich, you can tune the alpha, and when you play around the numbers, it will give you a different scores. Okay, that's called the hyperparameter search. So basically, it finds all the possible value for the parameters, and just try them all to see which one gives the best results. Okay. Okay. Everyone is falling asleep. So any questions on this part? How do you generally feel about machine learning? Is it still very confusing, or any idea?
I don't feel confusing.
Yeah.
I just feel there's a lot of work behind this.
A lot of work behind.
Yeah, and then at the moment, we are trying to learn how to do all those work.
Yes.
But obviously, there are a lot of resources on the internet that you can just plug and kind of push together.
Yes.
And that's the piece where I'm thinking about, okay, where can we find those information?
Okay. I think to start, best to go to sklearn.
Okay.
So sklearn is a website that has all the model. Okay, if you want to know the scope of what's all the model I can choose from, you can go to sklearn and just click like supervised learning, and you have a very long list of models that you can choose and play around. Okay.
But you also mentioned that we can do, sorry, I forgot the description.
The model selections.
Yes, exactly.
Yeah.
So I assume there should be somebody who already done similar things as model selection,
Yeah.
where it can help us to quickly go through all this instead of us understanding the joke.
I think that's the ideal case. The ideal case is we don't have to do anything. But if you go back to like the first step of the workflow, the first one is understand the problem. And the reason why we can't do it automatically is because every problem is quite different. Okay, you have some data set might have a lot of text, but not a lot of numbers. Okay, some data might have like multiple label, like not only 1 and 0, but you can have like jeans, jacket, clothes, laptop as your tag. And every model, some model that doesn't support like multi-tag, and some model performs better with multi-tag. Okay, so well, it's quite hard to do it automatically, I think, but it's still possible.
Is there a list where it talks about pros and cons of each model that we can search
Pros and cons. I can't think of a list right now, but I think the best way is go to sklearn. And well, I understand you shouldn't spend time to go through all of them, but yeah, because I learned it the hard way. I didn't. When I learn it, it doesn't have like automatic way to do it, so I have to do it that way. But I think I showed you guys this matrix before. Okay, this one is how well the model performs against the rest of the model. For now, like gradient tree boosting outperform most of them. So that's probably the first one you should start with. Okay. Okay, if you have no questions, then I can start by going through the regression homework. Okay. Did anyone have a look on the updated version of the homework? Do you have any idea what the homework is about? Okay. Okay, price one. Maybe the better way is I try to go through the homework in a step like this. And so you can just replicate the steps and apply it on a different problem. Okay. Alright, so just a basic introduction of what the problem is. Okay, the problem is I want to buy a laptop. Okay. And then I want to know the laptop I buy worth the money. Okay. But well, you know, laptop you have many specs, right? You have different screen size, you have different processors, RAM size. Okay, now I want to find if I input all the specs on the model, it should output like a fair price. And if the laptop I want to buy is more expensive than the fair price, then I shouldn't buy that laptop, right? If there are two laptops, the specs are the same, then I should buy a cheaper one, right? Unless like the brand names has significantly better value. Okay. So what I do is I try to go through all the laptops. Okay, I went to this website, and if you click into it, it should give you a spec table. Okay, so every laptop has a list of variables, like the processor speed and the processor brand and what's the operating system, etc. So these are the factors that contribute to the price. Okay. Okay, so first thing, I have to understand the problem, and then I have to figure out where to get the data. Okay, and I figure out I can get it from these websites. Okay. And I can go through all of them and extract the table, and I can have the specs for many different laptops. Does that make sense? Okay. And then, okay, And then you have to understand the type of labels. Okay, what are my labels in this case?
Specs.
Yeah, the label is not the specs. The label is the price. Eventually, I want to make a tabular data. Okay, so every machine learning model has to have a data that looks like this. Okay, you have a thinner one, which is the Y. You have the thicker one, which is the X. Okay. And in this case, what's my Y? My Y is the price. Okay, so every row should be one laptop, right? So this is like maybe $500. This is, I don't know, $4,000, etc. And then what's my X in this case? The specs, right? So every specs would be a column. So let's say this can be the processor, and this can be the RAM, etc. Okay. So that's the data shape that we want. So let's try to make this a shape out of our data. Okay. So if you look back to our data, it doesn't look that shape. Okay, it's just a straight table. So we have to try our best to make it look like that. Okay. All right. Alright, so let's go to like the step 2 of our workflow, which is the data preparations. We have to scrape the data from the internet. So this is the helper functions. So I just wrote it for you because I think it's time consuming. So if you do extract, oops, sorry, and you just put in the URL, it should return you something like this. Okay. So I just wrote the function for you, and once it inputs the URL, it just gives me a table in the format that is like one of the row in this data sets. Okay. So every column becomes like a features, and it's like MacBook Air. You have memory type, you have graphic card model, etc. Okay. And then I also have another data frame, which is this. I have the URL and the list of price. Okay, so this is every single URL, and this is all the price. Okay, then what's the next thing we can do? Okay, we have this table and we have the functions. I want to get all the specs from the internet. What I should do? What should I do? Yeah, just write a for loop through all the URL, and you can have a lot of rows, right? And you just combine the row, and you can get a data in this nice format. Okay. Okay, I would say in this workflow, I would spend the most time on the second step. Okay, I usually spend like 70% of the time just scrape the data and make it the right shape. And the reason for that is in real life, the data is very irregular. Okay, I try. If you go to websites, I thought every row would be the same, but then eventually, I figured out they just present different things for different laptops. Okay, so I have to clean it to make sure on every column is the same. Yes.
If you don't have a website list,
Yes.
that you have summarized in the Google Docs,
Yes.
then how can you make this selection as well from the website?
Oh, you mean how can I get this information? You mean? Actually, I do some preliminary work and scrape all of them. Okay, and how to do it is you can go to the content page. Okay, this is a content page. And if you scrape this page, you can get all the links. Okay, and then, well, if you play around, this is exactly the link that links to the next page. Okay, I personally do a lot of web scraping, so a lot of like big organizations actually hire people to do web scraping for them, and the thing is they hire people to manually get the data, and you can do it programmatically, and well, they find it very useful. So I think this is a very good skill to learn. Okay. Any questions for here? Okay, so if you run this loop, just change the number to like 3, and then just run it. And basically, what this does is it select one of the column, the URL column, and loop through every single URL, and then use something called a try catch. Okay, try catch means if it throws an error, it just skips it and go to the next step. Okay. For web scraping, it's important not to do it too aggressively, because they're gonna bend your IP address if you do it too fast. Okay. So now after I run the loop, okay, now I have list of many data frame. Okay, and every one of them looks quite similar. Okay, and if you check the type, every one of them is pandas, data frame, everything looks good. Okay, but then if you go through the shape of every single data frame, you can see they have different column counts. Okay, so that's the problem we encountered in step number 2. You have to clean and shape it to your desired format, which is this format. Okay. For now, it's not in this format, so we have to spend time and change it. So how can we shape it to this format if we have different columns? So now the case is we have a lot of rows like this, but the column like this one, the first item is the product name, and then the second one is like friend. But in this, the order is not the same. It's like product, and then storage. So you can't really combine these two because the column names are different. Okay. What can you do in this case? Okay, just change the order of the column. But what if this one is longer than this one? Let's say this has 23 columns and this only has 23. You can just create empty columns, right? Just create the empty one and then rearrange the order and combine them. Okay. So if this is smaller, I'll just add like RAM and then add something like I don't know, CPU, etc. Just make it the same length. Rearrange the order and stick it back. Okay. And okay, that's what I did. Okay, I just do a loops to find all the possible variables, and then this complicated steps is just to well, do what I just mentioned. And then this pd.concat is just simply pasting all the data frame one by one. Okay, and eventually I created this side of the table.
In this case, we care the name that the website gives is different. For example, one of them may address CPU, the other one may address the processor. But in this case, you may have the same data happening again.
Yes.
Do you care about this?
We do care about this because if that case appear, it will be on different column.
Yeah.
Okay, that increasing complexity. If you have to do it properly, you have to merge them. Okay, so that's why I say 70% or 80% of the time, it's just to make the data look like this. Okay, if you receive some data like this, you should be a very happy man. Okay, because normally data doesn't look like this. Okay. Okay, now we have something like this. Okay, it looks very clean, and then, well, you have all the like with USB ports. Okay, we're missing something. What are we missing? We miss the price. Okay, which is our label. And okay, what else do we miss? Any thoughts? So we didn't miss many things, but the data is not ready for modeling. And any clue why? Yeah, we don't know the type, and also let's say the width data. It shows us like 38.2 cm and 32.7 cm. Okay, what data type is this? Is this a float or integer? It should be a string because you have cm behind. Okay. And to quickly see this, I think you can do. And then, okay. So now you can see a lot of them are not a number, but a lot of them are objects. Okay, objects is not very good for modeling. So we have to turn it to numbers. Okay. Okay, so we are probably in the still on step 2, but we are like in between step 2 and 3 now. So the next step is we should try to do exploratory data analysis. Okay, but do we have domain knowledge? So say, do we have any knowledge between the relationship between RAM and price? We don't. Okay, I assume we do. So I didn't really do exploratory data analysis in here. What it means by is just do the pair plot and do all the visualizations for you to spot the relationship. Okay, I think we can try. Yeah, we can still try. Okay. Okay, so this is the data you should, the format you should expect to look like. Just go to step 3 and you can just straight away download the data I scraped. Okay. Okay, there's another issue with the data, which is a lot of NA value. Okay, so you have to clean it again. And this is especially hard to clean because you have like all the kgs and with like NA value. What would you do if there's a case like this? Wait, and then you have an NA value. Are you gonna skip the entire line, or what's the best way to do? If you throw this into the model right now, it's gonna give you error. So my approach is to find the mean of it and just reapply the mean to the model. Okay, but if you look at all the columns, we have 5 rows and 39 columns. Okay. If you put shape, okay, we have 190 rows and 39 columns. Okay, that's too many columns for the first model. So I'm gonna pick just 5, 1, 2, 3, 4, 5. Okay, 5 initial columns to make my life easier. Okay, I'll just do data. Alright, now it looks like a better format. I have width, USB port, processor model, and the memory type. Okay, and I hope this can contribute to my price predictions. Okay. So what I will do, I will just find the mean of the width and just add it back. Okay. Oops. Sorry. Okay, I'll rerun the whole thing. Okay, the mean width is 35.5, and I'm just gonna apply it to the data, and I'm just gonna fill NA with all the means, and then I'll fill all the NA with a blank space. Okay, now it looks something like this. So I have the width, I have the USB ports, I have processor model and memory type. Okay, so the first two is in numbers, so we're good. How about this two? This two is in what format? It's in string format, right? So what can you do to make it a number? Any clue? Nope. Okay, so now the step is we've done this, we've done that. So now we have a smaller data frame. These two columns are numbers, so this is numbers. And these two columns are string. Okay, so we have like DDR4. I don't know what's that, and then we have like DDR3. And then in the processor type, we have like 6Y something, 75, etc. So the model won't understand what's going on. Okay, what we want to do is we want to create a new column called DDR4. Okay, and then we put it 1, 0, 1, 0, 0. So for every combinations, we just create a new column. So we will have a column called 6Y75, and just 1, and the rest are 0. Okay. This is called dummy variables. Okay. And this is what you do when you have string data. Okay. But this will create something not very good, and that is create a lot of columns. Okay, you'll probably have more columns than your number of rows. Okay, let's see. Okay, so to create dummy variables, you just do data dot pd dummies, get dummies, pd dot get dummies, and then data. Okay, and then you can see you have a column called processor model 1505 something. Okay, and you have a very long data frame with 71 columns. Okay, if you check data.shape, okay, we have 190 rows and 71 columns. Okay, that's still acceptable. But if your number of columns is bigger than the number of rows, then you shouldn't do a model. Okay. Okay, now we have a data set looks like this. Okay, all numbers. Are we happy? Can we train the model now? No? What are we missing? Yeah, we should be able to train the model now. Okay. So I'm just gonna create my train X and train Y. And then I'll just implement my linear model. And I'm gonna get the score. Okay, my score is this. 0.86. Okay. Do you like the score? Does it look good? Quite good, right? But one thing to bear in mind is I'm using my fitting data, my training data to test. Okay, so it has to be good. Okay, if that's not good, then you're in a deep trouble. So what you need to test is you have to do cross-validation. Everyone remember what's cross-validation? What's cross-validation? Okay, you rotate your training data and test it on the one that you didn't use it to train. Okay. So let's say, okay, I do cross-validation score, and then I think it's easier to okay. So in one of the trial, my test score is just 0.03 and one is 0.51. Okay, that means it's very bad. Okay, and my data is not generalizing well on unseen data. Okay, so what can I do in this step? Let's go back to our steps. So now we're on steps 4. We build and evaluate our basic model, and we check on cross-validation, and the score is terrible. Okay, then what can we do? Yeah, we can do PCA. But what's the main reason for it to perform badly? Sorry, what did you say? I should twist around the features. Yeah, I can. But I think the main reason is I only select 5 columns. Okay. In this step, I just select these 5 columns. And probably, I only select with USB processor model and memory type. Okay. And probably you can't really distinguish the compare price with just these 4 features. So what you need to do is you have to add more features, include everything we have. Okay. And so let's try it with all data. Okay. We do this. Okay, now we have a very big data frame. Just do like spec.shape. Okay, just 24 columns. But we're now using all the 24 columns. I need to do some data cleaning because we have, these are all my columns. I have memory type, window version, graphic card model, webcam, etc. I don't want to go through them one by one. So just gonna quickly transform a weight and my battery life, which is here. Okay, so probably the longer the battery life, the more expensive the laptop is, I guess. And then, okay, now I just do a fill NA and get dummies. And my data is gonna be huge now, which is, okay, I have 356 columns after I do the dummy variables. Okay. And if you do, okay, and the reason why I have a lot of columns is because all my possible combinations are listed out as a column. Okay. So now what we need to do is to use a PCA. Okay. Okay. To create a PCA, we just need to do this. Okay, import the library, and then you have to specify how many columns your PCA wants. Okay. Normally, if you do it properly, you have to test all the combinations, like n components equals 3, 4, 5, 6, 7, 8. But for now, I'll just do 2. Okay. And then you do something like this, pca.fit. Okay, now you created a so-called PCA model. Okay, because you fit in your unseen data in, and then you do something like this, dot transform. Okay, now my 356 columns become 2 columns. Okay. And then I'm just gonna put it back to the data frame and rename the columns. Okay, so now I have something called XPCA, and I have all the product name and the just the transformed features. Okay, so now I don't really know what the number represents, but I know it describes this product. Okay. Okay. One very interesting thing with PCA, it's when you were in this stage, you have a lot of columns, right? And you can't really plot every laptop on the same same graph, because you have like 29 dimensions, so you can plot it into a 2D graph. Okay. But now you use PCA to make it 2-dimensional, so you can plot it onto a graph, and this is how it looks like. Okay, the first column, the first axis is PCA 2 and then PCA 1. Okay, and on this graph, the further away, it means the more different are between these 2 laptops. So I just plot the name. So I think this is like MacBook, and this is different brands. These are probably all the Windows, and this is probably some high-end machines. Okay.
So how are we going to use this graph? Because I don't know like what is PCA and what is PCA2, so like there's no meaning.
I think what this tells you is how different are the laptops. Okay. If you look at this, you would say these are more similar together than these. Okay. If you do something called clustering, so that's mean unsupervised machine learning, you can find out the groups across laptops. Okay, and let's say now I figure out these laptops are a group, and this is a different group. What I can do is I can add back to my regression line. So I can add like okay. I can add 3 more columns. This is cluster 1, this is cluster 2, cluster 3. Okay. And these laptops belong to cluster 1, this belongs to cluster 2, this belongs to cluster 3. Now I'm adding a stronger features based on what I observed. Okay.
Yeah.
And then okay, that's just an example for PCA. I hope that makes it easier to understand.
How do I know how many number of components for PCA?
For PCA, okay, that's a good question. If you go back to, okay, just go back to the previous PCA. Okay, we have something like this. Okay. So in PCA, every column means nothing, but it's just some pattern. Okay. But if you go back to this shape, let's say now this is PCA1, this is PCA2. Okay. What you can do is you can compare this and this, and you can tell the variance in this. Like how do the variance in PCA1 explain the price? Okay. And what this does is the variance explained per columns. Okay. And you can see because in PCA the first column explain the most variance. What I meant by explaining most variance is the pattern. Okay. Because if let's say you have the entire data frame. These features is actually a pattern. Okay, like it shows whenever the RAM is 8 GB and the screen size is 15 inches, the price is this. Okay, that's a relationship. And if you compress it, the variance in here is explaining the relationship of the entire data frame. And now what this means is how this column explain the pattern in all these columns. And you can see it is depreciating once you have more PCA columns. So it's just a matter of trade-off, like how many columns you want. Like if you go for a 6 column, it only explain like 3% of the variations. So probably you can skip it. Okay.
It's quite general for regardless of your data set.
Yeah, the shape is probably always like this. So probably people just go for like 4 or 5. Okay. It's just by feeling in here, not very scientific. So Okay, so that's it for PCA. But then remember we had something called lasso last time. So lasso is something called regularization. So that's mean dropping some of the column automatically. Okay, so if you run lasso, and how to run lasso is just do one line. Linear model lasso alpha equals 0.2. Okay, and alpha is a number that you can tune. It just means how aggressive do you want to drop your columns. Okay, so if you run it and you look at the score and you play around with the alpha, okay, and it gives you a higher score. Okay. When alpha is 0.2, it gives you a score of 0.8619. Okay, when it's a 0.1, it gives you a score of 0.8622. Okay, so if you do it for many times, you can find the optimal alpha you can achieve. What's the maximum and minimum? I think you can do from 0 to 1. You can do like, oh, sorry. Okay, and now you do a cross validation. Okay, still not great, like 0.4, 0.3, 0.2, but at least we don't see the case for 0.095. Okay. So you probably can see the power of PCA, how it creates value and transform some pattern to something meaningful. Okay. Okay, the last step is try to use lasso with PCA. Okay. So you can basically put this. Okay, so this is my PCA. I have my PCA1, PCA2. I can just directly throw this data frame to to that shape. Because now we are in our perfect tabular shape again. I have my train X and I have my train Y. So I can train my model. Okay. So just run it and then I'll check the score. Okay. If you compare the score, it looks a little bit lower. And the reason is for PCA, what's my PCA graph? Yeah, I only choose like 2 PCA, so I'm losing some explanatory power. But PCA is so handy, so it depends what's your use cases. Usually I just do PCA and it just gives a lot of hustle for me. Okay. So okay, that's it for my regression homework. Okay, if you're at work and then your model stays in this score, probably you get fired. Okay, so you have to explain to someone why the score is so slow. If you are the the data scientist, how would you explain the score in this case? Why can't I get 99%? Okay, the possible.
Branding.
Sorry.
Branding.
Sorry.
Branding.
Blending.
Branding.
Branding.
Yes.
Okay. Let's see if we have the brand. We probably have the brand. Okay, we don't have the brand. So probably that's a good reason. Like Apple computer sells way more expensive. I think the next thing I would say is we don't have enough data. Okay, there are more laptops than like 190 models. Okay, and Also, there are some factors we didn't put in, like the years of the model and the location where it's made. So just a lot of missing informations. So basically, what you need to do is you have to find more data. So maybe instead of scraping 200 rows, you scrape like 2,000, and you probably can build a better model. And or maybe you can just start to evaluate the relationship between the variables to see if you can create something that adds more value. Okay. Does it make sense for everyone? Okay. Are you sure everyone is fine?
So in this situation, I have to find more data, like, so basically I just have to create like a whole new model for it. Because pretty much all your data is from this website, so
Yes.
there's no other way for me to.
But I only scraped. Okay, let's go back up. Okay, so this is my data. I have around 3,000 columns, 3,000 rows, but I'm only scraping. I think I scraped like 200 rows, so I still have like 1,800 pages that I didn't use. Okay. I didn't scrape all of them just to save time. Yeah. So if I scrape all of them, then probably I can build a better model. Yeah. Any other questions?
So normally when I'm trying to build like this kind of model,
Yes.
should I like at first apply as much data as I have?
Yeah. So there's a difference between machine learning and stats. So for stats, you probably want to select the variables, okay, and take away those you think is useless. But for machine learning, you can just put a lot of noise into your datasets, and PCA probably just clean it for you. Yeah, so more data is always better, okay, generally. Are you planning to build some financial data? Or? Okay. How about the rest of you guys? Does it make sense, or it's very confusing?
Just one question about
Yeah.
the mean. When you usually use the mean, like in this case, we use it in the weight and the battery line.
Yes.
So, but in what kind of situation we use the mean?
Okay. Usually you apply when you have a dataset with a lot of float or integer. Okay. In this case, because a lot of them are string, so well you have to convert the string to numbers if possible. If not, then you just replace it with like empty string. And I think basically in most cases, if you have numerical data, the safest way is to replace with mean. Yeah. Unless, sorry. Yeah. Sorry.
Finish the question.
Oh yeah.
I have another say jockey club game.
Yes.
Every horse got their own data,
Yes.
like finish time,
Yes.
class of time.
Yes.
When it comes to jockey,
Yeah.
it's a different jockey.
Yes.
But each jockey
Yes.
got its own data,
Own what?
own data.
Yes.
So I put two data sets together,
Yes.
but then we repeat the whole thing.
You mean the combination of the jockey and the horse?
Yes.
Okay. Yeah, that's.
Plus another thing like finish time.
Yes.
Those things. What do you do?
Okay. Yeah, that's a challenge for pricing horse racing data. and the challenge is the jockey and the horse always race together, but it's very rare for the same jockey to ride on the same horse. So for every combination, you'll probably have like 1 or 2 sample size. Okay, is that what you meant? So I think we have like 300 horses and like 20 jockeys in Hong Kong. But every race, the jockey ride on a different horse. So if you look at the historical data, the chance of the same jockey riding the same horse is very rare.
But how do you differentiate which, since some of the jockeys are better than the others?
Yes.
But how do you put a score into that column, that jockey column?
Okay, so let me understand. So this is your jockey, this is your horse, and this is your ranking. Okay. And then let's say you have jockey 1 to 20 and horse 1 to 300. Okay, just to label them. Okay, 1, 2, 3, 4, 5. Okay, and then we have horse 100, 1, 2, 3, 4. But now we want to quantify this jockey, right? Okay, there are a few ways to do it. Because I'm very familiar with these data sets, and well, you can give a score for each jockey, and the way to do it is you build a dummy variable like that way, and then you put your y as the ranking, and then you can quantify how this jockey contributes to the ranking. Okay, but that one is not very meaningful. And the next thing you have to do is to do interaction terms called jockey horse. Okay, and you create something like this: 1 hyphen 100, 2 hyphen 1, 3 hyphen 2. So this column means how that 2 jockey race at the same time. And then again you create a dummy variable like that. And once you have enough data, you can quantify how good this jockey is and how good this jockey when he jogs together with the horse. Do you understand? But let's say if you stream it through the linear regression, you have the coefficient, right? And the coefficient means how good the jockey is.
If the data sets are separate,
Yeah.
you have separate data sets for the jockey,
Yeah.
and separate data set for the horses,
Yeah.
and you don't know how the interaction works.
Okay.
How would you multiply?